Conservation of momentum.
Here I go with a certain momentum. My momentum stops, but the momentum of the rest of the system continues on with enough momentum to make up for the momentum that I lost as I pushed off and landed stationary.
Conservation of momentum, inelastic collisions.
Okay, here we go. I'm going to jump on this cart, and then at the moment that I hit this cart, we have an inelastic collision. Now, just before and just after the collision took place, the momentum was the same because momentum is conserved. But finally, we do come to, the whole system comes to rest, and that is because in the process of rolling to a stop, I am imparting momentum to the Earth. So I actually changed the rotation rate of the Earth a little bit as I rolled to a stop. How about that? Okay, so this is this package here is going to have an initial momentum as I throw it to Mrs. Call. And then her initial momentum is 0. But then this will be an inelastic collision because she catches it. And so then just after the collision, the momentum will be the same as it was just before the collision. How about that? Good one. That was unexpected.
Conservation of momentum.
All right, Mark and I are going to exchange this cone. And as we throw it back and forth, notice the initial momentum of the system is 0. And so that means the final momentum of the system will also be 0. But we will start to repel away from each other. As that happens, keep in mind that this is the same thing that a positive particle would do with another positive particle, except instead of a cone, it's an exchange of a virtual particle. The result, the electromagnetic force. Okay, that's good.
And we will end on that note.
Okay, my mass is bigger, this mass is less, 0 initial momentum, so therefore my momentum and his momentum will be equal and opposite. But because my mass is bigger, my velocity should be smaller. His mass is smaller, his velocity should be bigger. In that last example, I guess my mass wasn't that much bigger than Mark's. And so let's try it again with a bigger mass differential. 1, 2, 3. Good catch. She's still moving.
Hello there, science enthusiasts. With me is amazing Dr. Seth, my lab assistant who does a lot of great demonstrations for me. And today we're going to do a crash course on collisions, and we're going to explore some very important scientific principles in collisions. Conservation of linear momentum and conservation of mechanical energy. And what we have is a standard setup here for a physics class, which is 2 equal mass carts on a level track. And we're going to first start out with some elastic collisions. And Seth, can we go ahead and start an elastic collision here? Let's have one cart with initial velocity at rest, and we'll see what the other cart that has a non-zero initial velocity does when it collides with that cart.
Watch this, guys. I just did something super cool. Watch this.
Whoa, that has 3 collisions. Okay, so let's go ahead and put the red cart at rest, and let's collide the blue cart gently. Okay, what we see is that the red cart has that velocity that the blue cart has, and the blue cart goes to rest. So they exchange velocities. Let's go ahead and, is this colliding stuff making you sleepy, Seth?
just tired.
Okay, let's go ahead and exchange velocity. Let's give both carts an initial velocity. Let's gently. There we go. When we do a collision like that, they exchange velocities and they exchange speeds and go off in opposite directions. Okay, let's try the other cart at rest. Okay, go ahead and collide. There we go. You notice that the red cart goes to rest and the blue cart inherits the velocity of the red cart. Let's put two equal masses on the carts. Let's put those 250 gram, they're approximately 250 gram masses on each cart and see what happens when we collide them.
Okay.
Okay. Let's
test
this thing.
Supposed to do this one?
Not quite yet. There we go. Let's go ahead and collide. Do enough. There we go. And let's make one at rest and collide the other. Oh, nice. Okay, we see it still holds if we increase the mass. What if you give the red cart more mass than the blue cart? Let's put both 250 gram bars on the red cart. Okay. And let's make it at rest and see how much easier it is to exchange velocities. Oh, no, it's the same. So now it won't go to rest. You see how that changes? And you can see what the final velocity is if you know their initial velocities by using conservation of linear momentum. All right, let's go ahead and do an inelastic collision. Dr. Seth, can you set up an inelastic collision for us? Without the masses on them?
Okay.
Okay. Nice job. All right. Now let's make one card at rest and give, let's say, the blue card initial velocity and collide. Now that's an example of a perfectly inelastic collision where linear momentum is conserved, but mechanical energy is not. And they stick together and move off with the final velocity. So let's go ahead and give them both an initial velocity in this case. And let's do a collision. They collide and stick together. And usually if one has a higher mass, what's going to happen is it will move in the direction of the higher mass. And we all could think of examples of like a semi-truck hitting a small little VW. In that case, if they collide and stick together, the collision will move off together in the direction of the semi because it's a higher mass. Okay, why don't we try some other little examples here? Let's go ahead and we've got some other toy cars with us that we could experiment with. We have some assessed collision cars. Oh, we got two same mass trains. I forgot about those. Can we collide those? All right, so there we have an inelastic collision, but in that case, it's a little harder to get it straight. When we conserve linear momentum, what we're looking at is a center of mass collision on top of the center of mass, which could happen in some cases, but typically, if we look at how car crashes occur, it's very difficult to hit the center of mass, and usually it ends up with a little bit of a rotation. Let's try some almost equal mass toy cars. Okay, if we have one at rest, there we go. We could see that the same principles hold. Let's say we have one of these carts at a stop sign. Okay, and then we have another car behind it. Okay, is that one going to collide with that one? Let's see what happens there. Okay, that one pushes the other one off in the opposite direction. Now, if you had another car, if you had two cars waiting at a stop sign at rest, and you put another car in, and one car comes zipping by, what happens? Oh, wow, you can see that there's a transfer of energy going on. Now, if this was all perfectly elastic, you could go ahead and find the final velocity of that car in that long line of crashing mobiles. So conservation of linear momentum is conserved in both elastic and inelastic collision, but kinetic energy or mechanical energy is only conserved in elastic collisions. All right, thank you for helping us with our experiment, Dr. Seth. Take a bow for science. We appreciate your hard work, even on the days you are tired. Let me see. Here's the equations you need. Seth. Here's the equations you need to figure out some unknowns. As long as you have enough information, you could solve for unknown velocities and unknown masses. Hello there, folks. With me is Assistant Seth Call, my science assistant for the day. He's one of my Call Science Boys team, here to demonstrate some traditional scientific principles in physics. Today, what we have here is, what is this called, Seth?
A ballistic pendulum.
A ballistic pendulum. Yes, this is a standard model you'll find in textbooks and in standard physics labs. And what we do is we look at how momentum, linear momentum, is conserved, and we use a little trick in mechanical energy conservation to figure out how fast our projectile is traveling. The projectile being this tiny mass ball. So we measure this mass, and we measure the mass of this pivot arm right here. As you see, here's our pivot arm, and there's a center of mass nodule right here. And so by knowing this mass, knowing the mass of our projectile, and measuring the height for which it rises up when it captures the ball upon firing from the spring-loaded launcher, we can figure out the speed of the projectile. Can you do us a demonstration without actually firing what happens there, Seth?
Yeah.
Okay, let's put the ball on the end of the launcher, which mass we know. It gets fired, it gets captured, so it's an inelastic collision into the pivot arm. The pivot arm swings up, for which you could find the height. So you could do some trig, and by knowing the angle here, you could figure out, you could use some trigonometry to figure out the height, or you could measure the height from the rest position to the center of mass. So here the center of mass is at, can you release the lever for a second? Here the center of mass is at rest, and then it gets captured up to a certain height. So by measuring that height distance, we could get the potential energy. So would you go ahead and demonstrate one run for us, Dr. Seth? There we go, and that's what happens. It gets captured. And what we do now is we do our conservation of linear momentum equations, and at the point of capture, we go ahead and look at the kinetic energy values and equate it with the potential energy values, and we use that to find the velocity of the projectile. And Seth Call really enjoys this device. In the traditional days, this would be a wooden block, and this would be a pellet or a bullet, and the bullet would fire into the block of wood, and the block of wood would rise a certain height. All right. Thank you, Seth Call. Thank you for your contribution to some physics understanding today.
Bye-bye!
Hello, students. Here we are again, going to explore more concepts in mechanics by experimenting with simulations and do-it-yourself projects at home. So we're going to cover some of the topics in this lab number 7. And this lab will cover concepts of impulse, energy, and linear momentum conservation. So we're going to review a lot of these theorems and concepts that you've learned in class. Some of the main goals of this lab are to explore energy conservation. So what we know with energy conservation is your initial energy is always equal to your final energy a little time later. So if we measure the amount of energy we have before something happens, it will equal the final energy afterward. Now the tricky part is identifying all the energies in your system. And the ones that we are capable of looking at are the mechanical energies we studied, like the translational kinetic energy, the energy of motion, which is 1/2 mv squared. The potential energy being the stored energy in the field, the potential energy from gravity, which is mg delta y. So we know that you give something a little bit of height with respect to an initial position, and it has a certain gravity difference between those two values. Okay, so we can have a maximum potential energy at the maximum height, and when we drop it, it falls to the ground, and that potential energy gets converted into kinetic energy. So we know our potential energy from gravity. We can use the mg delta y derivation, and we also have the energy of springs. So if you take a spring like this, it has potential energy. So it has energy stored in the spring, and that is given as 1/2 kx squared. This is the spring constant, and this is the distance that we have, the displacement of the spring. So if I let go, we can see that that potential energy, that stored energy in the field, is converted to the energy of motion. So we'll cover more of springs or elastic energy in future chapters. So even though we say energy is constant, total energy is constant, in our case, we want to look at the specific cases of kinetic and potential energy when there's no friction involved. Okay, we want to see how much kinetic energy is converted to potential energy and vice versa. Okay, we want to look at mechanical system. So when you set the work done by non-conservative forces to 0, meaning there's no friction or heat, etc., we can make this association. However, we will explore cases where this does not hold true. This is going to be non-zero, and we have some simulations and do-it-yourself project that will involve some energy losses. And then you have to explore where those energies, what type of energies those got transferred into. Okay, so really important concept. The total energy is constant. And then we're going to look at the work energy theorem. So it takes work to change the speed of an object. Okay, so you put work in and it'll change your kinetic energy. Important concept we'll look at. And a big one is linear momentum conservation. So when you hit something on the center of mass and there's no external forces involved, what we'll see is that the linear momentum before is equal to the linear momentum after the collision, or after something happens. Okay, so we'll look at this. So we have linear momentum, remember, is mv, mass times velocity. It takes the direction of the velocity, and these are all vectors. I was being a little loose with my notation here. Okay, so this is always true as long as we can box it up and add no external forces. So we need to know the difference between the elastic and inelastic uses of that conservation law. So when they're elastic, we have all the individual mass times velocities before are equal to all the mass velocities after, or the final velocities. Okay, so very important concept we'll look at. Okay, and then inelastic collisions, or when objects collide, they stick together and they move off with the final velocity. For two masses, mv1 plus mv2 initially should equal the sum of those masses moving off with a final velocity. So some very important principles here. And again, just to outline it, these are the main concepts, theorems we'll work with. And lastly, we'll look at the impulse momentum theorem. Impulse is all about applying force over a certain increment of time. If we look at F average times delta T, what we have here in our impulse momentum theorem is applying force over a certain period of time will result in a change in momentum. Okay, so we have many situations that involve the impulse momentum theorem. If you're playing baseball and you have a baseball hitting the bat, the baseball bat interaction, the baseball will result in a change in momentum depending upon, and this will be equated to the amount of force impacted by the bat over a period of time on that baseball. Okay, or if we throw a ball at a wall versus a piece of clay, we'll have different F delta T values, and we'll look at the resulting change in momentum to analyze that. So we'll look at these 4 conservation laws and principles. All right, so let's get to the different parts for lab. We have part 1 is simulations and part 2 is do it yourself. Okay. All right, there we got our call assistants here, and now we're going to go ahead and try some ball stacking and look at the impulse momentum theorem and some conservation of energy principles involved. So on the count of 3, Seth will drop this soccer ball and tennis ball combination, and we'll observe something very interesting that goes on here. So I'm going to count to 3 now. 1, 2, 3.
Oh.
Right. So for the first part of our lab here, the simulations we'll look at energy loss lab. This energy loss lab, and then we'll also do some of this experimentation on our own and see. We'll test different types of objects, different types of balls, and we'll look at the height that we drop it up from and the height it rebounds to. So in this energy loss lab, this will set you up for doing this experimentation at home. And what we're going to do is we're going to set this to Earth so that we have a specific amount of gravity acting on our objects. We set to Earth, and we're going to have a certain height of, let's say, 3 meters, and we're going to drop the ball on our energy. So we're going to measure from the bottom of our ball. So the first ball will be like a tennis. So we're going to drop a tennis ball, a hockey ball, ... We'll drop several of these, right? So, and you can sort of predict what's going to happen. So we're going to drop this, and we'll notice as it bounces off the ground, the type of ground will make an impact on how far it's going to rebound. So we need to think about it. And we're going to take this information, we're going to estimate the height it rebounds to. Okay, so this will be a rebound height, which we want to measure. Okay, so our height, our drop height, is at 3 meters, let's say. We got a rebound height, and then what we want is in addition to our rebound height, we want also the time to drop and the time to rebound. And we're going to get those measurements, and we're going to look at how much energy is lost in the process. So the big question is, E loss is equal to what? And which of these ball types result in the most energy loss? And when we talk about energy loss here, we're talking about mechanical energy energy loss, okay? Because what you want to talk about is really what that energy got transferred to. And notice that if you're doing this on your own, that you're going to hear certain sounds. If you're dropping a ping pong ball, for instance, you'll hear that sound, and that's energy leaking out of the system, or energy being transferred to sound energy in that case. In this case, we're saying sound, we're not including sound into our mechanical energy equations. So which ball types result in the most E, mechanical loss? And what type? And what type of transfer? So it should be simple enough. So some things to think about. Okay, the next simulation here is very common. This one we do in our actual labs a lot. It's something you could test out if you have a set of billiards at home. You could explore elastic collisions, and if you have a capturing device for a ball, you could explore inelastic collisions. So the second type of simulation, this is the cart collisions. Okay, so the second simulation deals with cart collisions, a real common type of experiment that we do in class when we meet, and we look at the mass ratios of the objects that we want to give momentum to, and we would look at the momentum before a collision and after a collision, and we go ahead and see if linear momentum conservation rules hold and if mechanical energy rules hold, okay, as well. So anyways, what we want to do is we do cart collisions in this second simulation, and we're going to have two different colored carts. So what we want to do is we're going to have a blue cart and a red cart. So I'm going to mark this as, here we have a red cart notated by R, and here we have a blue cart. Okay. And what we want to know and play around with is the mass of the red cart equals so-and-so. The mass of the blue cart equals so-and-so. Okay, if these are the same, we want to go ahead and collide these and see what the result is. And we also want to explore changing the velocity of the red cart equals a certain value, let's say initially, and the velocity of the blue cart initially equals a certain value. Okay, so what we want to do is, let's start with an elastic. We want to look at these cart collisions, and we're going to set the elasticity. Let's say part A, elasticity to 1, okay? Which means we're going to make a purely elastic collision. Okay. Then what we're going to do is we're going to set the elasticity to 0, so it becomes inelastic. Okay. So we have different types of these collisions. Like, we could change the numbers around, but we're going to make it purely inelastic, so that they collide and they stick together. So to begin with, we start with the same masses, and the important part in these problems is to take a look at what happens before and after. So we call that the initial situation, or before the collision happens, and then we look at the situation after. So in the initial stages, we're going to have the red cart is going to move with a certain velocity. Okay, so its mass velocity will have a certain momentum, linear momentum. And the blue cart will be at rest. So this will be the velocity of red initially. And this is the velocity of blue initially, which would be 0. Okay, so they come together, then they collide. So they collide. And then what happens afterwards, the final or after result would be what? If these are the same masses and this is elastic, you could predict what's going to happen. and you could see what's going to happen as you play around with the number. So what's going to happen in this case is if they collide, the red, and sorry my carts are not to scale here, the red will become stationary, they will exchange velocities, and the blue cart will go off in this direction. So this is a little snapshot afterwards. Okay, so this should go to 0, and this is 0 to begin with. Okay, so we'll see that exchange. Now the next part is, this is for part A, when it's elastic, very elastic. And then you could play around again with these. This is the case of elastic, the same masses. Elastic, same mass. Okay, let's double this mass, see what happens. Double this one, see what happens. Triple this one, etc. Okay. Now, if we look at the case where this is going to be purely inelastic, changing that elasticity to 0, let's go ahead and see what's going to happen. So now in B, when we say inelastic, okay, we're going to have the initial prior case. We're going to have, let's say, red is going to go ahead and collide with blue. Okay, so it has an initial mass velocity, so it's velocity of red, velocity of blue, which we know is 0 if we start with 0. But we want those initial values, record all those values, and then they collide and stick and move off together with a final velocity. So this is what we always want to recognize in linear momentum problems. It's wonderful when you have a linear momentum problem because you could always apply these conservation laws too. Okay, so what happens is we're going to get this red plus blue mass. And then what's going to happen is they're going to move off together with a final velocity. So I should shift it over a little bit. Red plus blue, and they move off with a V final velocity. Okay. Now what we know is in this case, the energy here, E mechanical initial is not equal to the E mechanical final. We're going to have energy, mechanical energy losses in that process. And unlike the elastic case, energy and linear momentum were conserved, but in elastic cases, linear momentum is conserved again as long as there's no external forces, but the mechanical energy is lost. Okay. So anyways, that's how we're going to do this simulation, since we don't have the carts at home. But again, you could explore this with billiards or bumper cars if you have them, or some other fun objects you could do. Okay, so the third simulation that we're going to look at here is Newton's cradle. And this is sort of a fun simulation, and Newton's cradle is this demonstration, this famous demonstration where we have all equal mass objects, mass balls, and what happens is if we give this a little bit of potential energy, which will give it some velocity as it strikes the other balls, we expect that the amount that the ball on the end displaces will be equal to the amount initially of the first ball. Okay, so we'll take a look at these simulations. We'll start with 3 pendulums, then we'll look at 5, and we'll change the elasticity. Now this demonstration right here, this demo that we have, you could see it's not purely elastic. It slowly loses some of its energy in the process. So the elasticity not all the energy is transferred there, okay? Or not all the mechanical energy is transferred, so we're losing some of the collision, we're losing some of the elasticity in the process. So go ahead and take a look at this simulation and play around with the different pendulum sizes. So just to kind of give you an idea. So what we want to do is elasticity equal to 1, number of pendulums equal to 3. So that we have 1 ball, 2 balls, and we take one of these and we want to look at what's going to happen as it strikes the rest. And think of our conservation of P. Conservation of linear momentum and energy. How's our energy conservation going for that as well? Then change and 5 pendulums, then elasticity to 1/2. Okay? So what happens as we decrease that elasticity? Okay, you could hear a lot of sound, the transfer of sound energy there. So you could hear the sound, which means that a lot of the sound energy is escaping out of the mechanical energy system. Okay, so what we have is changing this elasticity will definitely influence this, and what's going to happen is these are going to move together closer. So they'll go back and forth. So the less that elasticity is, the more that they'll sort of combine and move together. Okay, but here what you're going to get is you're going to get this last final ball. This is 1, 2, and 3. What we're going to get is 1 and 2 here, and 3 should move upwards, ideally, as much as 1 moved towards 2 in the purely elastic case. So some fun physics in Newton's cradle. Okay, the next simulation that we want to look at is the ballistic pendulum, and we will insert a little video clip of the ballistic pendulum that we make measurements with in our physical lab. But we'll do this simulation, the ballistic pendulum. Which is a wonderful demonstration on how conservation of energy and momentum go. This is a historical device used to measure the velocities of incoming projectiles. So what happens is the ballistic pendulum will have like 3 stages. So what you want to do is approach in 3 stages. So when you're looking at this simulation, you want to think of what's happening at the very beginning. So you have, let's say, you have the mass of a bullet, and we'll keep track of those numbers. Those are given to you in the lab. And then you're going to have the mass of the wood block, mass of the wood. So I'll just say W. This is going to be much heavier. Will equal a certain value. I'll write it over here. Mass of the wood will equal a certain value. So what we're going to do is we're going to have the mass of our block here. The mass of our bullet. So this is our bullet right here. And then we're going to have this wood block that's suspended from a string. At a certain height, okay? So here's our wood block. Now this is going to have a velocity. We're going to have an initial velocity of the block will be so-and-so. The initial velocity of the velocity of the bullet initially will have a certain velocity. The bullet will initially have a velocity. Okay, there we have it. The wood block, however, will be stationary, be 0. So our next stage is 2. What's going to happen is this bullet will move and embed itself into the wooden block. So in stage 2, we have the mass of the block plus the wood. Okay? And then the very next stage is the fact that they will move together now as it embeds. It will move together and rise a certain height. So you're going to have to pause the simulation and find out this delta y, or the height value of how far it moves. Okay, so you're going to find this difference right here. And what happens is we'll move up to this value. Delta y. And they're both moving with mb plus mw move with a final velocity. Okay, and the reason I broke this down into 2 stages, so I should really say mass of the block plus mass of the wood here. Okay, so what you want to analyze here is playing around with these numbers, the mass of the bullet, the mass of the wood block, the velocity, the initial velocity of the bullet, and see how that changes everything. And typically your main goal is to figure out what the initial bullet value is. What is that going to be? Okay, based on what these masses are, and based on what you measure for your delta y. So your delta y, or your height, equals so-and-so. You take that from the simulation. Okay, so the important things here are, what we have is momentum conservation holds true throughout the entire process. Okay, so the initial momentum, we know Pi equals Pf, okay, throughout the whole process. And that's steps 1 through 3. Okay, so what we could say is mass B plus mass wood times, these are both initially, mass of the bullet times the velocity of the bullet plus the mass of the wood block times the velocity of the wood block initially will equal mb plus m wood v final. Okay, so we can use that. Now we won't know what this final velocity is, and we don't know the initial velocity of the bullet. We do know that that's going to be 0, so that crosses out. So this should go to 0. Okay, so we're going to use conservation of linear momentum. Again, remember these are vectors. And number 2, we're going to look at stages 3 and 2. So if we look at 2 through 3, what we'll see is that even though energy is not conserved from 1 through 3, we can apply energy conservation in these last 2 stages. Once the bullet's embedded, its conservation of mechanical energy holds. So again, when I'm saying conservation of energy, I'm meaning conservation of mechanical energy, because again, energy is always conserved. So the amount of kinetic energy this mass of bullet, this bullet and wood block system have will be transferred into potential energy. So what we do is we look at this stage, we use conservation of energy. We say the change in kinetic energy plus the change in potential energy must equal 0. And we use this information, the 1/2 m, the combination ma plus b, m total, mb plus mw, v squared. Okay, so that'd be v final squared will equal the mb plus mw, the total mass, m little g, the acceleration due to gravity, delta y, how far up it climbs. So we'll use this in combination with this, apply your knowledge in how to solve systems of equations to find the initial bullet velocity. Okay? So use these two equations to do that. All right, and the very last simulation we'll work with is impulse. Applying the impulse momentum theorem. So the last simulation, impulse momentum theorem. I'll put this in parentheses because we're really looking at impulse. And this simulation takes a look at applying a force over a certain period of time. So what we're going to do is you can experiment with your F applied equal to so many newtons and the time that you're going to apply that force, okay? So it's like if you collide certain objects, the time in that collision will impact this impulse. So the time F is applied. And that will equal so many seconds. In this simulation, you're going to play with different values here. And then what you're going to do is you're going to record the data from the graphs you get. So every time you change your force applied and the time, you're going to have a certain graph. So for instance, if we do, let's do our F applied equal to 5 newtons and our time to be 2 seconds. What we want to do is we're going to use to find the change in our momentum. What's the change in momentum here, which is what the impulse is. So what we're going to do is we're going to look at our momentum versus time graph. Okay, and if you pick those two values, you're going to have a graph that, here's our time in seconds. And here's the amount of newtons. So this will be our force in newtons. And we're going to find that what's going to happen is we're going to have a certain amount of force. And then as we apply that force for a 2-second interval, we'll see this little climb. And then it'll become constant again. So we're going to see this change in our momentum. And excuse me, this is my momentum versus time. Okay? So our momentum versus time curve might be something like this. We measure a certain amount of momentum based on these values. Okay? Or it's given to us in the graph, so we'll have to look at the scale. And remember, momentum is we're looking at mass times velocity, so we're looking at the units of kilograms per times meters per second. Okay, and then it'll tell us for how many seconds it goes. Okay, so we can see this is the time frame the impulse is applied. All right, so that you want to explore how impulse and change of momentum are related. So before, when we were looking at impulse, the way we find it is force. It's the integral of force dt for your initial time and your final time. A lot of times we could look at impulse data. We could look at how forces interact with objects over a period of time, and we could take the area under the curve and find the impulse value. So we're going to compare some of our graphical data in the lab to that concept. Okay. So lastly, our second part, our last and second part, is exploring some of these concepts on your own. So what we have is our ball drop, ball, and energy. I'm going to have to gather up some, 2 or more, hopefully more, so you can explore this. And again, we're going to do this, we want to relate to the energy loss simulation. And it's really hard to time if you don't have a partner to do this. But what you want to try to do is measure out a scale. We measured a scale of 2 meters outdoors, and we dropped it from 100 centimeters or 1 meter, 1.2 meters, etc. So what you want to do is have a certain drop height, like let's say this is 1 meter, and you drop a tennis ball, see how much it rebounds. Okay, if you get the timing, it's great. So what we have here is we want to see how much energy loss is involved. So we have ball 1, and then we want to do a ball 2 type. Okay. Maybe now we have a ping pong ball on hand. We'll drop it and we'll see how much it rebounds. And then maybe we have a super ball. We'll see that the rebound height is really good on that. So we want to do it with 2 different ball types and 2 different surfaces. Okay. So if you're looking at rebounding a ball off a hard surface like concrete, you'll get a better rebound height. You'll get more energy that's conserved, mechanical energy. However, if you're going to rebound off a softer surface, maybe some carpet, grass, you're going to find that you're going to have more energy loss. Okay, and that's the main one. So you're going to have ball drops. And 2, we're going to look at the work kinetic energy. We're going to change the speed of an object, and try to keep more to the textbook standard of K instead of KE. So those are typically interchangeable, meaning kinetic energy. And what we're going to do is we're going to construct a pendulum. And you want to keep your apparatus, your pendulum apparatus, because we're going to use it in future experiments some more. And you want to give your pendulum some energy, right? So you're going to have some potential energy max, U max, and we want to dump that potential energy into kinetic energy. So we're going to get that to do maximum kinetic energy. So we're going to make a pendulum, and then we're going to collide as best we can with the center of mass of an object. Okay, and that's typically hard to do. But if we take an eraser like this and we want to try to get this eraser to move, or let's say a box, typically a box with not too light, but a wide enough box so you could try to hit on the center of mass. If you get it to collide, you could get it to move in a straight line path, which is what you want to do. So you want it to collide rectangular mass, and then you want to see how far it goes. And the v final velocity, we want to see how far it goes and how much of that velocity was transferred into that object. Okay, so we're going to try to get this on as centered as possible and move in a straight line. Okay, so we're going to experiment with those concepts there. All right, that's it for now, and we'll have some video clips to add in here. All right, but just before we go, we have a student here with us that wants to ask a few questions. Okay, questions. All right, Miss X-Ray is with us here today, and looks like she has her mask on, being very considerate. And what's your question, Miss X-Ray?